This is part 1 of lesson 4 of unit 7, covering logistics, growth, and Newton's law of cooling. These two concepts are just relevant on the BC exam. They are not on the AB exam. And the reason for that is when we go to create our general equation from our differential equation, we're going to have to use a concept not on the AB test, which is partial fractions. So just a quick review. We've already talked about several forms of differential equations. The ones that usually fall into word problems can be categorized into 4 types. First, our position, velocity, and acceleration, where our acceleration is a constant, and when we integrate it, we'll get velocity, and when we integrate that, we will get acceleration. The second type we covered in the last lesson, which is simple growth and decay, where your rate of change is directly proportional to the amount present. So we get a differential equation such as y equals ce to the kt. And we talked about that in lesson 3. Now in this lesson, we're going to talk about 2 different types of exponential growth. And they have to do with, well, one's not exponential growth. Newton's law of cooling isn't really exponential growth. It is exponential, but it's not necessarily growth. But logistics growth is a more realistic form of exponential growth. We have talked about this in pre-calc, is that you have a limit to how much something can grow based on space, available resources, that sort of thing. And so the population is limited by the carrying capacity or the limiting factor. And that is usually our L, which is in the numerator of our logistics function. And you can see this is the same form of logistics function that we worked with in pre-calc. Now what we're looking at is the form of the differential equation, how it looks before we get to that form. So it's important that you guys get used to this form. You're going to see the differential form. And if it's a multiple choice question, it would be great if you didn't have to actually do the differential equation, find the antiderivative, that you can skip right to the formula itself. So that's a way to save some time for you on the test. But anyway, I'm going to go through here and I'm going to show you how you solve the logistics equation, where K and L are positive constants. And I have a list here of steps that'll help you go through the procedure. So the first thing is to separate our variables. So we're going to go ahead and do that. And going to multiply both sides by, if I distribute the p, I'm going to multiply by both sides by 1 over p times this this factor of 1 minus p over L. So I'm going to do that on both sides. And when I do that, I get, and of course I'm going to switch my dt to the other side, I'm going to get dp over p times 1 minus p over L. And I'm going to get k dt here. Now I'm going to rewrite that fraction so it looks like this. So I am going to have the integral of L dp over p times L minus p. The reason why I want to do that is now I have 2 factors that I can use to do partial fractions with. So now what I'm going to do is I'm going to look at L over p times L minus p. I'm going to write that as a over p plus b over L minus p. And then using our little shortcut, I'm going to let p equal 0, and looking in the original fraction, so I'm just looking at, so I'll have L minus 0, so I have L over L, so that leads me to a equal 1. And then if I let p equal L, so I get a 0 in the second one, again I'll have L over L, which will be 1, so b will be 1 as well. So now this is what I'm integrating. I'm going to write this as partial fractions. I'm going to have the integral of dp over p, that's when a is 1, plus the integral of dp times 1, which would be b, over L minus p, and that's going to equal the integral of k dt. Okay, finding the antiderivative of both sides. I'm going to run out of room here. I may have to move over to the side. I'm going to get ln of the absolute value of p plus ln of L minus p is going to equal kt plus c. Now what I'm going to do, and what you want to, the reason why you want to do step 5, multiply both sides by -1, is it makes solving for p a lot easier. So when I do that, what happens is that ln of p becomes negative. Oh, actually, here's why. I'm sorry, this should be a subtraction here because I have this negative sign. So I want this to now be a positive, so that makes these two a negative. Okay? So what I get then is I can write this in this form, ln of L minus p over p equals negative kt minus c. And so what I can do is I'm going to continue down here. Taking e of both sides, I'm going to have L minus p over p equals e to the negative kt plus or minus c. And rewriting that, that is going to be, I can call that a e to the negative kt, because a is going to equal e to the negative c. Okay, so now what I can do is I can solve for p. So if I multiply the p to this side and divide that, okay, and then I'm going to add p. So I have a lot going on here. So let me just go up here. Let me rewrite it. So I have L minus p over p equals a e to the negative kt. So cross multiplying here, I have L minus p, I'll just leave it this way for now, equals pa e to the negative kt. Now putting our p's on the same side, I have L equals p plus pa e to the negative kt, factoring out of p. Now solving, I get p is going to equal L over 1 plus a e to the negative kt. So there's my formula. Okay? And now, one little note here is that if you're trying, a quick way to find your a is dependent on the initial condition, which we have done in the past, but you can find it very quickly by taking L minus p sub 0 divided by p sub 0. Okay, so looking at this a little bit, what we're going to see is things to remember here. Our carrying capacity is the maximum population that the environment can sustain. So that means as p approaches 0, dp dt is going to equal to kp. Okay, and then as p approaches L, dp dt is going to approach 0. And if you look at the graph, what we're talking about is the fact that as we get close to L, remember dp dt is the slope. We have a horizontal tangent line there. And as p approaches 0, we're looking at the idea that we're kind of along here a little bit on this side. Okay, so let's label our graph here. So what we have is that horizontal tangent line is our carrying capacity. And a thing to note here is that it is concave down through this part of the graph. that would come up in like a part C of a free response question. You'll notice there's a point labeled here. This is our inflection point, and this is also the point where it is the steepest. So this will be where the maximum slope is. That's the steepest part of the graph right there. And then as we come to this point, what we find is the limiting factor is less involved. So we really kind of have an exponential curve here. Your classic exponential behavior. But then what we're going to find as we get past this, past that point of inflection, we end up being concave up. So we do have a point of inflection. Okay, so this is called the logistics curve. In logistics growth, the population grows the fastest when the population is half the carrying capacity. So what we're talking about is the max of dp dt is going to equal when p is half of L. And the slopes are small near our two horizontal asymptotes, so one near p equals 0 and the other one at p equals L. They're steepest at the inflection point. And that is at p equals L over 2. Okay, so what happens if p is greater than L? What's going to happen here is we know it usually curves off, but in real life nothing is perfect like that. But what's going to happen is the slope will become negative. And the reason for that is the population is going to decrease. Because that's as big as you can get it and maintain it. Remember, that's maintaining that population. But if you go past that, that's when you have species dying out because they're overpopulated and you end up losing species. Okay, so reading features from a slope field with a logistics function. So here we have a slope field for a logistics function, and it's modeling the population of coyotes in a wildlife preserve. They have done studies, and they know the preserve can support no more than 100 coyotes on the property. Write the differential equation with k equal to 0.1, where t is measured in years. Well, the nice thing is that we know L. So L is 100, and we have our k. So we can use our differential equation, which is kp times 1, whoops, I forgot the 1 minus p over L. So if we fill in what we know, our differential equation becomes dp dt equals 0.1 p times 1 minus p over 100. Okay, the slope field is shown at right. Where does the horizontal asymptotes appear to occur? So right here at 100, you can see it. Those are pretty much horizontal. And also at, we're almost there, but not really. You can't see it on this graph. We're going to end up, we can't really have negative time. So in real life, we don't really have, because I'm sure coyotes were already present. So there really is only one in this real life situation is at y equals 100. What happens if the initial population is above this asymptote? So let's say that we have this preserve, they know it'll hold 100 coyotes, but someone gets a bright idea, well, let's put 120 in. So what would happen is if it's above that asymptote, the coyote population will decline. Okay. If the preserve initially begins with 20 coyotes, sketch the graph of P of T on the slope field. All right, so we know we're going to go through 20 here. And we're allowed to use our calculator for this. So if you put this in your graphing calculator, I'm just going to use the 84 because it comes up faster on my computer. You can do the same thing on your Inspire. So what we're going to have here is I'm going to put my differential equation in here. What I want to remember is you're supposed to just sketch this, so I'm just going to go ahead and sketch it. I kind of did it ahead of time. I cheated because I know from my form that P of T is going to equal 100 over 1 plus 4e to the negative 0.1 t, because I could find A by taking 100 minus the initial population of 20 divided by 20. So I got A was 4. Whoops, it doesn't look like a 4 at all. But we're going to do that in the next section on the next page. But if we were just to sketch this, it should look something like this. Just want to follow the curves that are there, because that's what they're there for. So it should look something like that without getting into details. I guess I kind of cheated when I did mine. It's like, oh, I can use a calculator. That's fine. So we're going to go ahead and find that general solution and the particular solution for 0. All right. So going through the steps of doing this, even though we have the answer, and hopefully that on the test you won't have to do all the steps. D of P over dt is going to equal 0.1 P times 1 minus P over 100. So rewriting this, we're going to have dP over P times 1 minus P over 100 equals 0.1 dt. Okay, and then doing our partial fractions over here, if we rewrite that like we did before, we'll have 100 over P times 100 minus P. And we can rewrite this now as A over P plus B over 100 minus P. And using our little trick, if we let P equals 0, then looking at our original function, we're just looking at 100 over 100, so we get an A of 1. And if we let P equal 100, so we cancel out that part of the denominator, we'll have 100 over 100, so we get B equals 1. So they both work out to be 1. So what we have now is we have our integral of dP over P plus our integral of dP over 100 minus P equals our integral of 0.1 dt. Okay. So when we do this, we're going to get ln of P minus ln of 100 minus P. And remember, you need that negative because there, when you take the derivative of that, you'll have a negative dP, so that was missing. And this equals 0.1 t. Okay, using our little trick before and changing the signs of these. Oh, of course, we have our plus c here. We're going to end up with, I don't want to use the red. ln of 100 minus P over P equals A e to the negative 0.1 t. Okay, cutting a couple steps out there because we already did those before. Then what we're going to do is take e of both sides and then simplify it. So we have 100 minus P over P equals e to the, I got ahead of myself here, I'm sorry. Sorry, I was skipping steps, I shouldn't have done that. This should still be negative 0.1 t minus c. I got ahead of myself in steps there. Okay, so now this is going to be a e to the negative 0.1 t. And now solving this for p, rearranging everything, we have, so we're going to have 100 minus P equals P times AE to the negative 0.1 T. So we're going to have 100 equals P times 1 plus AE to the negative 0.1 T. And if you're not sure what I did, go back to earlier in the video. So solving for P, we get that P of T, this is going to be our general solution, is equal to 100 divided by 1 plus AE to the negative 0.1 T. Now here you can use the idea of knowing that P of 0 is 20, and then solving this for A, because that'll go to 0. This part will go to 0. The E part will be e to the 0, which is 1. And then solving this, you get that A is going to equal 100 over 20 and then minus 1, so you're going to get the 4 that I came up with earlier. So our particular solution is going to be P of T is going to equal 100 over 1 plus 20 e to the negative 0.1 T. So there's our general and our particular solution. All right, so next part. When will the coyote population reach 80? So we just have to use our equation now and solve it for 80. Forgot the 0.1. Just hit. Okay, and so you're going to have 1 plus 20 e to the negative 0.1 t is equal to 100 over 80. And so we get 1 plus 20 e to the negative 0.1 t equals 5/4. Multiplying through by 4, you get 4 plus 80 e to the negative 0.1 t equals 5. Solving this, why do I have a 20 there? Sorry, you guys, I completely wrote this incorrectly when I wrote my general solution, because I apologize. I got A is 4 here. Here, see 4. So this number should be a 4. So sorry. So when I come down here, this number will not be a 20. It'll be a 4. This should be a 4. I was like, wait a minute, something is not looking right here. So these should be 4s. So that should be a 4 and a 4. And then when I multiply by 4, I'll have 1 plus 16. Okay, and then, so now I get e to the 16 e to the negative 0.1 t is going to equal 4. So e to the negative 0.1 t equals 1/4. And then solving this, I'm not going to belabor the steps. I get t is approximately equal to 27.7 years. Okay, so when is it growing the fastest? Remember, that is when P is equal to L over 2. So that is going to be 100 over 2, which would be 50. And then what you're going to do is go through the same process here, substituting 50 in our equation. And solving for T. And when you do that, you guys can go through and do that yourself and double check my answer. You should get 13.82 years. And then finally, we're going to, in the next video, talk about Newton's law of cooling.